Hello to everyone, I am Baiano Svizzero and I'm giving you some lessons about computational acoustics with open source software, specifically FEniCS. So let's start. First thing, we are going to design a geometry, and of course we are going to start with something very basic. So I can open my FreeCAD software, create a new project, and let's say that we just want to solve a very simple geometry like a cube or a parallelepipedic geometry. So what we can do here is to at least have different dimensions. We see that we have a very small volume, so let's make it a bit bigger. What do you think about 300 millimeters, 400 millimeters, and maybe 250? So we have this very simple parallelepipedic shape that we can export. We go on File, click Export, and then we can name it Air Volume. You can name it as you want, of course. Let's click OK. This format is going to be OK, and we can exit FreeCAD. Our next step is to mesh the geometry we just created. So we can open gmsh. We can go on File, Open, click import our just created geometry, click OK, and we will see the geometry. If this doesn't happen, we can double click on the empty space, click on mesh visibility or geometry visibility, and check what is not going to be shown on here. We can click on surfaces and we can find our geometry. You can notice that if I go on some of the faces, I see the ID of the geometry faces. So we see surface 3 and surface 4 here identified as plane 4. This is pretty important since we are going to assign some boundary conditions on these surfaces. So let's remember that we are going to apply one boundary condition on plane 4 and one boundary condition on plane 3. This is very important since we are going to assign the physical grouping on the gmsh API. So let's quit. Let's open one Python script. Let's create a new Python script that which name will be let's say measure.py. In measure.py we have to first of all initialize some of the needed modules like gmsh. We could need also the standard sys library and os library, so let's import that. Import sys. And that's all. So let's initialize gmsh. I'm noticing that it's better to zoom on the script for maybe your eyes. Let's give this model a name. Let's call it air mesh. Okay, let's call path the variable that encapsulates the actual path of the working directory. So it's pretty straightforward. You can just copy these lines. and then we can just merge our geometry. Okay, there's a mistake here. Okay, everything is fine. Now we're going to specify the units of our system, so we are going to go with meters. Then we are going to assign some basic mesh size value. There are a lot of them, but we will stay pretty good with the standard mesh size max parameter. So since it's basically a parallelepipedic geometry and we don't need to, you know, refine in some areas or little sub volumes, we are fine with that for now. Let's say that we are fine with 3 centimeters. So this is in meters, of course. I've done a mistake here. Okay. So it's very simple. So let's create the physical group relative to the volume. In this function, we have to specify the dimension of the geometrical entity. For a volume is 3. The geometry ID, that is 1, and then the mesh ID that we are going to give it to it. We can choose any number. We will give 1 just because we like it. Then we can give it a name just to be recognized in the future. Now we are going to do the same thing for the surface entities. Let's just copy maybe this part 2 times, and we are going to assign the following IDs to the 2 surfaces on which we want to apply boundary conditions. That will be a velocity boundary condition and an impedance boundary condition. So for a surface, we have a geometry of dimension 2. The first surface entity was the number 3. We will give it a number 2 for the mesh ID, and we will call it velocity BC. The same thing can be done for the other one, which ID was 4. We'll have a mesh ID of 3, and then we will give it a name. Okay, now everything is done, and we can generate a mesh with the following command. In which the number 3 stays for which mesh are we going to generate. Do we want a 3D mesh, a 2D mesh, or a 1D mesh? Then we are going to write the generated mesh with the following command. We will give a file a name. And we are going to display what we just done. So with the fltk command. finally we will finalize gmsh. We can run the script. We will see that we just generated a full 3D mesh. If you want to see it more, in a more detailed way, we can go on mesh visibility, check 3D element faces, check, uncheck 2D element edges, and then we can use the clip option in tools clipping. We just select mesh, and then we have a plane that we can use to clip our mesh or geometry. As you can see, as I go further, we see the clipped mesh and how our mesh is going to look inside. Since the geometry is quite simple, this is going to be uniform and everything is going to be, okay. So this is the clipping command. We can exit and we can highlight the physical groups we just created with the visibility window. We can click on velocity BC. You can see that the plane tree is highlighting with this red cross, and the same thing happens to the impedance BC, which is set on this other plane. Okay, so this mesh has been created. The file is here. It is full. It is ready to be used by FEniCS. So let's start scripting our FEniCS script. So let's clear our terminal. I just created a Python file which name is direct frequency response. We are going to perform a direct frequency response just like you would do on a commercial software. So we are going to set our boundary conditions, our material properties, our microphone location, and we will just plot our graph. In the end, we will also look at a basic usage for a ParaView visualization for the acoustic field. So let's go through all of this. We will need a lot of modules here, so let's import NumPy. And let's just import all the modules needed for the Python script. Okay, now that our modules are imported, let's just try to run the script. For complex analysis, we have to source our FEniCS complex mode. So the folder is, oh sorry, the folder is the following. And then we can run the script. Let's save it. Okay, I made okay, there is an error here, of course. Okay, let's save it and let's run it. Everything is fine, so we can go ahead. The first thing that we will do will be import the gmsh generated mesh with the following command that will give us 3 outputs. The first one is the mesh entity, the second one is the cell tags, the third one will be the facet tags, the third one will be the facet tags. With the module gmsh.io dot read from msh, the first input is the name of our mesh file. The second one is the MPI communicator setting. For now we are not going to need this, but anyway, let's set up world, and then let's just tell to FEniCS that this is a 3D problem. Now, since we are going to make a direct frequency response and solve our problem in a frequency spectrum, in a frequency range, let's define a frequency range with an numpy arrange function. So our frequency axis would be numpy arrange, let's say between 50 and 1000 Hz with a 5 Hz step. Let's also add comments. So this is creating a frequency axis. Then we are going to define our trial and test functions. First of all, we are going to create a function space with Lagrange elements of order 2. Then we are going to create trial and test functions. Next thing is to specify a mic location. That will be, let's say, an numpy array. Let's say just random coordinates that we are sure that are in the volume, within the volume. Okay. Then let's define the material characteristics for our problem. We will have air. First one will be sound speed. This is meter per second. Then we will define the air density. This is kilograms per cube meter. And that's it. Now we will define K0, that is the acoustic wave number. Since we are going to change it through the analysis, it's pretty convenient to initialize it as 0 or 1 or whatever you want with a constant function. We have to give it the mesh entity and a PETC scalar type of whatever value you want. Let's say 0, for example. First thing, we are going to define the normal velocity boundary condition. So we will assign a random value. Let's say normal velocity we will assign a value of 0, 1. This is meter per second. It's a pretty high value, I know, but it's just a linear problem. You can put whatever you want in here. Then in the second part of the video we will add also an impedance boundary condition that for now will be air impedance, in a free field, that is 0. Okay, sorry. Okay, I'm wrong here. Okay, next step, let's save. Let's just run to see if we made any mistake. Yes, we did. Yes, we did, and of course there is a mistake here. Read from MSH. Let's do it again. Of course. This is what happens when you write your code from scratch. But we are doing it because I think that this is what you will do in the first time. You will find these errors and mistakes here and there. So let's save it and run it again. Everything is fine now. Okay, that's how you write code, guys. Make mistakes, correct them. Now we can add the definition of the bilinear and linear forms. This is the very beautiful thing about FEniCS, that it allows you to write code in the same way of weak form equations. It's an interesting way to build an FEM solver. Okay, we need to, since we are going to apply some boundary condition on the physical groups that we just created in the gmsh, we need to specify that the differential ds has to take as inputs the faces tags that we just imported here. So this is how it's done. With this, we can start writing our weak form. So the bilinear form is the following. As you can see, we see here the inner product between the gradient of u and the gradient of v, where u is the trial function and v is the test function. We also have a dx, and this is just what you will see in the weak form of the Helmholtz equation. So we also have the mass part, the acoustic mass part, that is k0 squared times the inner product between u and v, of course, times dx. And then that's it for the bilinear part for now, since we are not going to apply an impedance boundary condition right now. We are going to build the linear part, but I just noticed that we need also an omega constant. Just copy this one. Let's initialize it. Since we need that later in the for loop, we need k0 and omega to change for the updated frequency. So let's put this into the bilinear form. I'm assuming that you know how the weak form is written. If you want to know more about that, more about theory, let me know in the comments. I will do a dedicated video. Okay, so the velocity boundary condition comes in the linear form in this way. So it's j omega times dot 0 times Vn. I see a mistake here. Times v, that is the test function. Now, since it is a velocity boundary condition, we don't have to use the dx but ds, and we can specify on which surface it is going to be applied, just retrieving these IDs that we give to the surfaces before. So the velocity boundary condition will be applied on the surface 2, on the physical group 2. Okay, this is a very cool way to write it. You just write the S of 2 and it will assemble this vector only on the surface that we created in gmsh. So let's go ahead. Let's create the empty function that will be the container of our solution. So will be just another function on the function space v. We will give it a name. We will see this name later. Then we will use the linear problem module. That is an easier way to initialize a PETSC KSP solver in FEniCSx for a linear problem. So you can do this with the standard PETSC4Pi API, but the FEniCS guys created this very cool module. We just write a linear problem and we give it various inputs: the bilinear form, the linear form, the PETSC options. That has to be included in curly brackets. So we will define the KSP type. Let's not make mistakes here. Will be pre-only. Sorry. Then we will say. Then we will define PC type. We will choose LU factorization. Finally, we will choose the matrix solver type. That will be the well-known MOPS. Okay. Just to be sure that everything is okay, let's run the script another time. Okay, no errors, no mistakes. We need to import a multiprocessing module from which we will import the pool function. This function. So let's just copy and paste. I'm not going through the details of this, but just know that the main function is this, the map function, where the inputs are the frequency loop function that we are going to define and the input of the frequency function. So NF will be the the frequency index of our of our frequency axis. So we are going to define a frequency function like this. So as you can see, the map function will take the input NF from this defined range that is just the range of the indexes of the f-axis array and give it to the frequency loop functions. So we are basically going to solve the linear problem for a set frequency. So this will allow us to solve the problem for multiple frequencies in parallel. And this will need a lot of RAM, but unlike the domain parallelism, this is going to scale perfectly. So if we double the cores, we cut in half the computation time. So where do we decide how many cores are we going to use? So how many processes are we going to use in parallel? Here you see when we define the pool function, we give a number that is the number of cores. I'm setting 3, but you can set whatever you want. So let's define the frequency loop function. First we need to assign to the constant value of k0 the current value that depends on the index of the frequency axis. So we are going to take NF and just use it to select the wanted frequency. Since we are taking frequencies, we have to transform them into wave number, just multiplying 2 pi f over c0. Okay. This takes the frequency that we are analyzing and multiplies by 2 pi and divides by c0. The same thing, we need to do the same thing with omega. That is just 2 pi frequency axis. Now we can just solve the problem by using the solve function included in the linear problem module. And that's it. This will be enough to solve the problem, but we want more. First of all, we want to export some or all the fields, the acoustic fields. So for example, let's export an acoustic field in XDMF format every 100 Hertz. So it's very simple. We can just ask if f-axis and f is a multiple of 100. So this is the remainder, has to be 0. And then we open an XDMF file, giving it the communicator, the wanted name, we are going to give it a name depending on the frequency it is referred to. So f-axis and f plus .xdmf. Select the writing mode. So we just open the module and we can use the function write, mesh and write function. And that's it. Now the last thing that we need is to take the value of the microphone that we located here in this position. And this is quite not straightforward in terms of how many commands we have to give it. There is no automatic function that gives this, but we can just copy and paste this code. Just do that. This basically takes in the coordinates of the desired point, builds a bounding box tree around it, then compute the colliding cells of this bounding box tree, and knows where in which cell, tetrahedric cell, the point is located. So this allows us to use the eval function, knowing in which cell it's located the point and the point itself. So it gives us these p-values, let's call it in this way, that is just what we want, giving it the MIC location, so the MIC coordinates, and the input mesh. So you could just put all of this in a function, and that's what I do, but I wanted to show this code that you find on the FEniCS tutorial by Jorgen Dokken. So we can go ahead, and this is it. The last thing that we are going to do is to export the spectrum, just to, for example, analyze it in another computer or another day, just to have it saved on our disk. So let's save it in the standard format, that is a frequency column, a real part column, and imaginary part column. So let's just call REP, it's the real part of PMIC, and then the imaginary part is computed in the same way. Then to save the txt file as CSV file, we need to stack these columns, so we'll define a stack array. And then finally we can write our CSV file. Okay, now that we wrote that, we just want to also visualize it at the end of the computation. So let's import matplotlib. And let's create a figure where we plot the spectrum. We are going to plot the spectrum in dB format, so the formula is pretty straightforward. 20 times the base 10 logarithm of the absolute value of PMIC divided by standard value, 2 times 10 to the minus 5, and then that's it. Let's show it and everything should be okay. Let's run the script. Oh, there is something that is not okay. Of course it has to be numpy log 10 and should be fine. Okay guys, I just noticed after the solution that I forgot. Of course I'm making mistakes, so I'm human, and we have to add which function will be the solution of our problem. So we just have to put u equal uh for our output function. So let's run the problem. As you can see, it's creating the fields files for every frequency, and we have a spectrum. So this is the spectrum. You see the resonant frequencies, and that's it. We will have also a CSV file where we find real part, imaginary part, and we can plot it in another software, maybe Excel, MATLAB, whatever you want. Now let's open ParaView and let's see how we can visualize this field. Let's open one of the frequencies, let's say 800 Hz. Let's click apply. Of course, the real part, there is no real part since the problem has only imaginary input, and that's it. This is the acoustic field at 100 Hz. We can visualize another frequency, for example 900 Hz. Let's click apply. Let's choose real pressure, EMAG pressure, I'm sorry. That's it. We can also visualize it through contours. So if we click contours, we can select a different range calibrated on the EMAG pressure. For this case, let's open the linear intervals. Let's set it to 20. Let's generate and apply. As you can see, we have the contours for the isosurfaces of the acoustic field. Of course, you see these like rough surfaces, since our solution could be more accurate, but this is just a matter of refining the mesh, or giving a higher polynomial order to the elements. So just some tricks for the ParaView visualization. You can change the interpolation light algorithm. You can change transparency and opacity like this. You can give it a metallic behavior, as you can see. Reduce the roughness so it seems like a metal. I really like to make something like this, like giving an opacity driven by values, like let's go in edit and enable opacity mapping for surfaces. So as you can see, the blue is going to be more transparent than the red, and maybe we can invert this behavior. Let's close this. We can go at this point in the bottom of this menu and enable ray tracing. Let's choose OSP ray path tracer, and here is how I set up my simulation, and how I build all the visuals that you see on my LinkedIn profile, maybe, or in my previous videos here on YouTube. So we can augment the sample per pixel, like maybe 5 is enough to remove this noise from the image. It will take some time, maybe. Yes, and now the image is clearer. Let's disable the ray tracing, and that's it. This is how to build a FEniCS solver with a velocity boundary condition, and I'm going to include an impedance boundary condition in the next video. I think that now it's getting quite long. I mean, this part is getting quite long, so let's cut it here. And thank you for watching. Don't forget to subscribe. I've got a lot more lessons coming your way. If you're looking for a tailored course, or maybe you need some custom code for your project or your analysis, don't hesitate and contact me. I will put all the links below. I want to remember that we are specialized in acoustic and structural model analysis, vibroacoustic frequency response, and even thermoacoustic frequency response. So the links are below. Thank you for watching.